talk to you about the interface between power and control. Now, you all know that modern power systems are one of the greatest scientific achievements of the 20th century. Huge generation and distribution and use of power is one of the things that has defined our world. But the world's changing, and we're now believing that we should move to different forms of energy: renewable energy, solar, wind power. And those new forms of energy are very different from traditional systems. And so, although I've said that the power systems are the greatest achievement, one of the greatest achievements of 20th century science, we now face new challenges. And the new challenges have to be met by new technologies and new ideas. And of course, one of the key enabling technologies that we're going to use is that of industrial electronics, or power electronics. They're going to be the core technology that allows us to interconnect new sources of energy with users. But in turn, that leads, I think, to a related question, because the traditional methods by which we controlled and regulated our power systems are going to change. And I think we have to change our thinking about the way that we regulate and control our energy generation and distribution. And so I think now we're going to have power systems, power electronics, and control very closely connected together. Now, I'm a control engineer. That's where I started from. And it's only recently that I've become involved in this area. And so it's very appropriate that I tell you about people I've been working with. Some of these have been here. I think Galina gave a talk at this workshop last year. Brendan McGrath comes from RMIT in Melbourne, Australia. And Chris Townsend is a young man who works with me. But there are many other people that I want to acknowledge. Pat Wheeler, who's visited our university. Marco, who's been a great help as well. So, what does a control engineer think about power electronics and the generation of power? Well, I'm going to take a very simple example just to show you that control thinking is important. And the problem I'm going to look at is that of harmonics. So one of the issues, of course, with the kind of loads that we're connecting and the way that we generate the power is the profusion of all sorts of harmonics. So my colleagues asked me, well, this must be a simple problem, Professor Goodwin. How do we get rid of harmonics? And indeed, I said, yeah, it's a simple problem. The first thing you need is an observer for the things that you want to eliminate. So this is a harmonic observer. And then to connect that to the system, to the power electronics infrastructure, using some optimization tool. And model predictive control is one that many people in the power electronics community have embraced and are using. Of course, we need to take account of the fact that it's a switched input. Only a finite number of switching states are allowable. But that's not too difficult. And there are hundreds, thousands, maybe hundreds of thousands of papers on that in the power electronics area. So what I set myself the task of doing with my colleagues was to eliminate a number of harmonics. And you can see here that I've said the 5th, 7th, 11th and 13th harmonics. And these are important in grid-connected applications and in drive applications. Fine. Now the principle is easy. What one does, this is the quantization due to the power electronics. And if you then pass the difference between the voltage that you would like to have and the one you actually generate through some sort of filter, an observer, and feed it back, then you should in principle be able to get rid of any harmonic you like. So the basic idea is to choose that filter shown on the last slide here, this H of Z, as a resonant filter which has a gain of 1 at the harmonic you want and has low gain elsewhere. And so if you want to eliminate 6 or 7 harmonics, you just put 6 or 7 of these in parallel or series. Very easy. Okay, so this is the sensitivity function of a idealized simulation. So this is the gain on the vertical axis, and on the horizontal axis is frequency. And you can see that in principle this works fantastically. We've got deep notches at all of the desired frequencies. In other words, whatever harmonics are being generated by the power electronics at those frequencies are eliminated. The thing you've got to be careful of, and this is one of the first things that I teach my students about control. It's a well-known idea. It's the Bode integral. And that is that if you reduce the disturbance impact at some frequencies, it needs to rise somewhere else. But the very nice thing about these notches is that they're very narrow, and so their impact on the total harmonic distortion is minimal. Now this is great. Terrific. So my colleagues implemented this on this simple back-to-back inverter, and with great excitement we waited to see the results, and of course I was absolutely certain this would work. Well, this is the resulting spectrum in the output voltage, and you can see rather than eliminating harmonics, actually the harmonics have been made larger. Now this is a big surprise to a control theorist. And so kind of my talk, my simple talk today, is really to bring these results, which are power electronics observations, together with some simple facts from control theory. Well, everything I'm going to say is summed up in this picture that you would see in every course in feedback control. So what are the elements you see in this picture? Well, because the input is discrete, it's sampled, there's got to be some sort of hold that applies those inputs to the physical system. At the output, so then there's the physical system. Then at the output of the physical system, we always have an anti-aliasing filter. Sometimes explicit, sometimes implicit in the A to D converter, but it's always there. And then there's the sampler. And connecting this sampled output to this sampled input is your favourite control system. All the elements that I'm going to talk about are in this picture. So this is the outline of my talk. I'm going to talk about numerical issues, fractional delays, folding, and that'll be the end. So let's begin with the numerical issues. This is the continuous time transfer function of a highly resonant filter. A filter that has gain of 1 at omega I and has more or less 0 gain everywhere else. Now, this is a high Q filter in continuous time. And it's traditional in all control. It's very common in this community, but it's the thing that's done everywhere. It's just to use Euler integration, right? To replace derivatives by a first order difference. So if you look at the bottom of the screen is a discrete time implementation of that continuous filter. Well, this doesn't work. And you might say, but you've just told us that this is the most common thing that is ever done, and it's true. But I'm also trying to do something a little bit more sophisticated because I'm trying to eliminate a whole set of harmonics, and that's a bit tricky. So, if you've ever done this, if you've ever implemented a high Q filter in sampled form, it's quite tricky. It's quite tricky. Okay, so a key observation is that we normally use shift operator or Z transforms or Z transforms, depending which country you come from. And Euler integration, which just says that e to the a delta is approximately I plus a delta. And as I say, it works for current control loops, it works in process control, but it doesn't work with these very high demanding feedback systems. And this is not a new thing I'm telling you. This has been known for a very long time. Actually, do you know that the very first work on sample data systems, which go back to Newton, were done using using what's called, I call the delta operator or incremental forms, right? And so, and actually what went wrong was Z transforms took us away from what Newton knew was the way to do things. So let me show you the right discrete form of this filter. And it's very different. I'll show you immediately. This is the one we had a moment ago. That's the one you get from Euler integration. The one on the top is a little bit more sophisticated. But this is the correct one. This one uses incremental form. What does incremental form? This state is a function of the past state plus a function. And this has vastly superior numerical properties. This buys you about 10 extra bits of computational accuracy. And if you don't believe that this is right, if you do a Taylor series expansion of this funny cos, you indeed get this. But in order to get this to work properly, you need to be a little bit more careful. Okay, so that's the first thing, numerical things. And you can read, there's a whole literature on numerical issues in sample data control. I can send you my book. I've just written, well, about 3 years ago, I wrote a book with a Chilean boy, Juan Yuz, on this topic. Okay, so numerical issues. Now, this one is even more of a surprise to me, I must say, but this is fractional delays arising from the commutation of this and the switching of the currents when a switch closes. The switch doesn't close automatically. You don't want to have two switches closed at the same time to give you a short circuit across the power supply. And also, depending upon the size of the current, etc., there's a need to discharge the power electronic devices. And so what more happens is that you get these fractional delays. Now, when my colleagues first raised this with me, I truly thought they were joking, because the fractional delays were 1 or 2% of the control period. And that can't be important. But then I suddenly realised that the harmonics that we were talking about, especially high harmonics, were 1 or 2% of the fundamental. And so this 1 or 2% of the fractional delay was of the same order of magnitude, relative size, as the harmonics. So this is also a cause of problems. And once you recognise a problem, I think the hardest thing is to ask the question, not to answer it. And once this question becomes clear what the problem is, the solution is easy. We have the tools to do this. In model predictive control, instead of predicting over one interval, do it in 2 steps, one over the fractional delay and then complete with the new control. And that can easily be done, and you can implement model predictive control or even more classical control structures once you've recognised this 2-step idea. So this is important, and that helps. But there's one more piece to the puzzle, and this one is the last piece that I'm going to talk about, and this one is the smallest piece, I must say. But that's folding. We know that sampling always produces folding, and so the anti-aliasing filter is very important. And since I'm talking about very high performance control here with elimination of very high harmonics and difficult things, then folding becomes important. Now, like all things, I said that using incremental forms for sample data control goes back to Newton, and the Laplace transform, the original logarithmic tables could only be generated by incremental forms. Equally, of course, folding has a rich scientific history. Borel had all these ideas in the context of, actually in the context of probability. Some of these names, I'll go back. Some of these names you will know, some of them you may not. The folding ideas were due to Whittaker, 1915. Of course, they're mostly attributed to Nyquist, and the formal proof of the folding theorem was done by Claude Shannon. And like many developments in the world, there was a parallel development in the Soviet Union, and this gentleman also understood and proved the folding theorem in Russia. So what's the idea of folding? Everybody learns this as an undergraduate student, right? If you sample, the spectrum gets folded back. So this is a picture of folding. Right? All the extra bits of the spectrum get put back in what you might call the visible range. This is the visible range after you've sampled. Now, usually we forget this, not important. But if you think about the controllers that I've just described, which are aimed at bringing the spectrum to zero, or make it very small at certain frequencies, and I'm using a sample data controller, I'm talking about the sampled spectrum. Sampled spectrum, not the continuous spectrum. So let me illustrate that there's a difference. This is actually a simulation of an inverter connected to a motor with saturations and so on to deliberately introduce high harmonics. And you can see those large harmonics are present in the current, these lines here. Okay, so that's with no compensation, and this is with discrete compensation, sample data compensation. See how marvellous it is? All of these harmonics have been eliminated. There's probably at least 10 or 20 dB attenuation of the harmonics. But this is in the sampled spectrum. What if you calculate the spectrum with a different sampling rate? Well, then you get this. And what you can see is the harmonics are actually there. It's just that they're not visible in the sampled spectrum. So what's happened is that this sample data controller has brought the discrete spectrum to zero. But all that means is that the sum of the spectrum, folded spectrum, is zero, not the real spectrum. So how do you get around this? Well, you need to think a little bit more carefully about the anti-aliasing filter to stop folding, or at least to control folding in some way. But if you do that, you have to remember now that those strong anti-aliasing filters are going to be the source of significant phase shift. And phase shift is the enemy of feedback control. So you've got some problems. But with these three things in mind, does it work? Well, this is what I showed you before. This is the earlier experimental results. And you can see these lines that were meant to be eliminated in the spectrum were not. And this is more recent results taking account of numerical properties, where you've got a 12th order controller with 6 harmonics being eliminated with high Q filters, accounting for numerical issues, accounting for fractional delays, and worrying about the folded spectrum. And you can see you can get these things to work. So that brings me to my conclusions. High performance control does depend upon attention to details, and it's wonderful because we have the tools to address this, but it means that people have to work together, control engineers, even communication engineers. Communication engineers know more about folding than any of us do, I think. All right, so, often Euler approximations, which work well in simple control, don't work well if you're trying to do something very sophisticated. Numerical problems do play a role. Little things like fractional delays and folding. But my bottom line is, if you're careful, you have the right team of people, which is usually a multidisciplinary team, then these things are easy. So, thank you for your attention.